Our task is to design a high-voltage direct current offshore converter platform. HVDC converters are needed for wind farms far offshore where electrical losses are too significant to use alternating current. The platform is to be designed with focus on reliability and efficiency, considering the harsh offshore environment and the sensitivity of the electrical equipment in the converter. We have identified main risks in our project related to reputational, operational, and project risk. A risk appetite statement has been formulated with an overall low to medium risk appetite. The tolerance of risk related to equipment damage and safety during maintenance works is low, whereas the tolerance related to environmental impacts is very low. Rough sizing and load calculations have been used to develop our initial topside and substructure designs. Initial values for wave loading were found using linear irregular theory, whereas the wind load was calculated using Morrison's equation. We will further improve these figures using CFD analysis and higher order theories.
The first design is a jacket, which is a steel truss structure. The jacket is constructed onshore and shipped to the desired location. Once the structure is in position, the piled foundations are installed. Finally, the topside structure is lifted into place. The disadvantages of the jacket structure are mainly related to difficulties in the pile installation and corrosion. The next design is a gravity-based structure. The columns will be made of hollow steel to ensure that the structure floats. The structure will be built onshore, floated to position, and sunk by self-weight and ballasting. This structure's advantages include simple construction, quick installation, easy removal and decommissioning. However, it requires a scour blanket and can suffer from corrosion. The concrete caisson consists of a heavy concrete base and a single large column. Construction is done onshore, ensuring a watertight caisson. The structure is then floated into place and sunk by pumping water. This structure offers good performance in low temperature conditions, however there is higher risk of foundation settlement and decommissioning will be complex. The jack-up structure has 4 steel trussed legs. The substructure and topside are built onshore and then towed to position. The steel legs are lowered to position and the topside is jacked up. This structure can be quickly installed and decommissioned, however the shallow foundations do not provide strong overturning resistance and there is a risk of punch-through. The tension leg platform is a floating platform which is held in place using mooring lines. After the anchors connecting the cables to the seabed are constructed, the structure is floated and fixed to position. This structure does not require much infrastructure. It is mobile and can therefore be used in multiple locations. However, there is a risk of cable fatigue and it provides better results in deeper water. The subsea solution is one where the HVDC components are placed on the seabed. This structure has no space constraints and eliminates most external loading. However, construction, installation, and maintenance are highly complex. Unfortunately, the technology for a subsea HVDC converter does not yet exist.
We have developed 3 different designs for our topsides. Our first topside proposal is a simple large box with rounded corners which houses all the required equipment. This solution is spacious and provides easy access to the whole converter. The disadvantages are mainly related to high wind loading. Our second design is a dome shape. The dome design would significantly reduce the wind load. However, construction and installation would become more difficult. The aerodynamic shape would reduce in-deck loading and drag force. However, construction of the dome is complicated and requires a large surface area. The box unit design consists of several box units with rounded corners, aiming to reduce the wind loading taken by the structure. This solution would have a higher deck area to substructure ratio, but construction is more complex and connections between units can be very problematic. The construction and installation phase is a crucial part of the project. The electrical equipment is very sensitive to movement and will need to be secure during transport. There should be no installation of electrical equipment offshore. The crane vessel required to lift the topsides offshore is one of the largest in the world and its availability is limited. Therefore, it is best to eliminate or reduce dependency on such vessels. Shallow foundations generate minimal installation noise, but may not provide enough tension and lateral load capacity. The foundations applicable to our designs are concrete gravity foundations for the gravity structure and jacket structure, suction caissons installed by self-weight and suction by providing differential pressure, and jack-up connections for the jack-up structure.
Deep piled foundations are often used when soil strength increases with depth, which is the case on site. We considered 3 types of piles: driven, drilled and grouted, and screw piles. After thorough research, we believe driven piles would be the most adequate option for our situation. Driven piles are by far the most used foundation option for offshore structures. In order to decide which foundation option is the most adequate for a particular substructure design, we will need to perform further calculations and research so as to optimize numerous parameters including cost, reliability, easiness of installation, environmental impact, and of course resistance to axial and lateral loadings. An initial estimate of the total project cost amounts to £500 million. The main variables in this figure are related to the material installation costs. The installation cost is dependent on whether we need a large crane vessel to lift the topside in place offshore. Substructure costs depend on the use of steel or concrete.
There are numerous environmental impacts which we need to account for in our design. These include installation noise, aggregation and erosion of sediment around the base, creation of turbidities, disposal of wastes and structural components during construction and decommissioning, and finally, creation of electromagnetic fields.
A possible top deck layout is shown here. A hole is reserved for the AC switcher that connects to the transformer hole. This feeds into the DC switcher that sends the DC current onshore. The final compartment is reserved for the maintenance personnel. A system of vessel access and retrieval is provided. This is an initial layout that will be improved as time progresses.
Moving forward, Team MVP recommends the following. In terms of the substructure used, we believe that the most viable options are the steel jacket and the steel gravity-based structure. Both of these options have been used successfully in the field of HVDC offshore. The topside designs we will be moving forward with are the mega box and the box subunits. Refining these options will enable us to provide the best possible design.